Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Mohit Bhardwaj with us today. Hey, Mohit.
Hello, Frank.
How are you?
I'm good. How are you?
I'm doing fine. You raised your hand there. Did you break your hand or you just got some warmth on?
Oh, I'm so sorry. So it's like you can see
Mm-hmm.
the inner that I'm wearing, it has this hole so you can get your thumb out. So it gives you some warmth.
Okay. So let me go there. What's your geolocation? Where are you at?
So currently I am in Montreal and Canada. So it's a very famous city in Quebec and the second most populous city in Canada.
Cool.
And I'm a PhD student at McGill University.
Okay, I'll take both of those. So you're already putting some things on for warmth in Montreal. So does this mean that there's already snow coming down in Montreal?
No, it's not snowy right now, but I must say the winters has arrived a bit earlier than expected because it's right now it's 8 degrees Celsius and it's cloudy. So it's cold, definitely. Okay. Yeah. So that's why there is a extra layer of what you call clothes to really prevent.
So I'm in Phoenix on this October 19th of 2021 when we're recording this, and it is very far away from 8 degrees C. We'll probably go up into the 30 C's, something like that, or something today at peak. So it's pretty warm still in more southern latitudes, at least in Phoenix in the desert. So where are you in your grad student trajectory? Are you about 1-2 years out from graduating, or where about you?
So I'm in the final year. Yeah, I'm in the final year of my PhD.
Awesome.
Yeah. So
well,
yeah, stressful times.
I look forward to congratulating you on being Dr. Bhardwaj.
I'm also looking forward to that part.
Let's see. Awesome. That would be very cool. So congratulations.
So do you also have autumn season in Phoenix, like colorful trees? Autumn season.
We have cactuses. We have cactuses and ironwood trees. So there are seasons in Phoenix. Yeah, for one, there's the wet season in the summer. So the summer is when it rains in Phoenix. And so it drives the humidity up a little bit. But we don't have the traditional seasons you might get in more northern latitudes where you have, for example, oak trees that turn colors or aspen trees that turn yellow or something like that. So we do have seasons, but they're a bit more nuanced. Yes. Some say it just goes from warm to hot to back to warm. So it's we do get a lot of Canadians coming down, snowbirds coming down into Phoenix. Like January, February, we get a lot of Canadians coming down to enjoy the fairly mild winters we do get in Phoenix. And then when it gets too hot, they go back up north to Canada. So.
No, actually, I'm from India, in Delhi. So it has similar temperature. Like it goes very hot, 48 degrees Celsius, and then it goes down to perhaps 1 or 2 degrees Celsius. It never snows there, but then it goes again.
You must be in the northern, you're from the northern part of India?
Yeah, so capital, New Delhi.
Okay. Yep. Very cool.
Yeah.
Very cool. What do you like to do for research?
So in my PhD, I am actually working on something very interesting, which I'll be talking in a while. And that is the phenomena called fast radio burst. Now, the question that actually interests me a lot is to understand their origins. What are fast radio bursts? What causes them? And what are their progenitors? So these are some of the questions that I'm interested in answering. Cool. And for that, I basically use nearby FRBs within our local universe that are detected by a revolutionary radio telescope in British Columbia, Canada, named the Canadian Hydrogen Intensity Mapping Experiment, CHIME in short. So I use nearby bursts detected by CHIME, and I follow up them and basically locate or identify their host galaxies and then study their nearby environment and then see what can cause them and what are the sources. And yeah, so that's what I do basically.
That's going to be an awesome thesis, I think. And that's going to bring us to this very lovely article, APJ letters, a nearby fast repeating, let me try that again, a nearby repeating fast radio burst in the direction of M81. And Mohit, take us away.
Yeah, thank you very much, Frank. Now, before I discuss about this article, I would just want to tell you that the FRBs are actually, so they were accepted as a true astrophysical phenomena only in 2013. So before that, people, actually astronomers, had this doubt whether they are man-made or whether they're actually astrophysical, whether they're extragalactic. So it's only after 2013 that we, as a community, accepted that these are alleged astrophysical phenomena. And but still, the problem is we have detected a lot of FRBs thanks to CHIME, who actually has detected over 80% of all known fast radio bursts. So there was a time when the number of models to explain fast radio bursts is more than the number of actual detections at that time, but CHIME changed the scenario completely. But the problem is with CHIME, we are not able to actually locate their host galaxies, and it's because the localization region is 20 or 30 arc minutes wide. So in that case, there are many sources. So you can actually say whether this particular galaxy is the home of this specific fast radio burst. So it's still a very big mystery that what causes fast radio bursts, these intense radio phenomenon. Now, for your viewers, I'll just give you a 30-second quick definition of fast radio burst. Now, the name fast radio burst is actually a very good, description of these events. So these are extremely energetic burst of radio waves that we believe are coming from far away distances, like cosmological distances. And there are like pulsed emissions, which last only for a few milliseconds or even smaller or shorter duration. And so just to give you a comparison, it is 100 times smaller than the time our eyes takes to blink. So it's very fast. And if you go to figure 2 of this paper, you can actually see how these FRBs look. I'm sorry, I'm changing the...
All good.
But I think it just for the visualization. Yeah, figure 2. Yes. So figure 1, I'm so sorry.
All good.
My bad.
Figure 1.
Yeah.
Yep.
Yes.
Yep. No. Frequency versus time. Yep.
Yes. Exactly. So what you can see here is x-axis is time and y-axis is frequency. And now we call these figures as de-dispersed waterfall plots. Now waterfall because it's just frequency versus time, and de-dispersed is because what happens that when these radio waves travels through the interstellar or intergalactic medium. So we have, it's a very tenuous, but we still have electrons, free electrons there. And then when these radio waves interacts with them, so what happened at that moment is the lower frequency is delayed more than the higher frequency. So it's basically Thomson scattering. And exactly, so what we see is if for example, our telescopes detect these waves as highly dispersed radio signal. So we have to correct it. And how we can correct it, because we know these signals, actually this dispersion follows frequency to the power -2 effect. So, so that's where you can actually correct it. And after correction, you see it as a single pulse, as you can see on the top of each of these subplots. And yeah, there one, exactly. And then it is not it is not like a spectral line, which is just located in a specific frequency. It's wide, it's broadband, as you can see in the case of, for example, third figure in A, exactly. And what happens is one big advantage. So how we say that these FRBs are extragalactic, because we already modeled this. We have a good idea about the contribution of Milky Way to this dispersion.
Right.
And when that dispersion is, when the observed dispersion for especially FRBs, we see those dispersion measures or this smearing is significantly larger than what you see in the case of a Milky Way pulsars. So we believe that basically is the strongest evidence we have so far that these FRBs are extragalactic. Now, the problem in this case is, if you look at the dispersion measure of this FRB, and for that you can actually go up. So I think it's table 1.
Table 1.
Yes. So the problem.
Table 1.
Yeah.
There we
Yeah.
go.
Table
Big,
1.
long, big wide table.
Yeah.
Yep.
So as you can see, in this case, the contribution, the DM is basically a quantity that quantifies this smearing. And you can see the DM is very small. It's around 88 units. And so what is the maximum that we expect from our Milky Way disk to contribute in the specific sight line? So this FRB has the galactic latitude around 42 or something. So it's really high. It's above the Milky Way disk.
Okay.
So the contribution we expect is low from the disk. But the problem is Milky Way also has this halo, which we actually poorly understand. We're still trying to understand how much ionized gas is there and whether it can contribute significantly to the dispersion measure of FRBs. And the thing is, you have a whole lot of models, like from simulation to like indirect measurements using spectral lines and all that. And they suggest that the DM can be as low as 10 units or as high as 80 units. So in the sight line, the Milky Way contribution is 40 units. But if you actually consider models that predict that the DM could be as large as 80 units, then this FRBs is definitely not an extragalactic source. It should be in the Milky Way halo, a wandering, isolated object. Now, that was a big trouble. I think a big challenge especially in the case of in trying to understand the origin of this FRB. Okay. And that actually makes this paper interesting. Now, this paper, when you look at, so once another advantage we had with this FRB is we detected multiple bursts. So we know that this is a repeating FRBs from the same direction. And for some of those bursts, in this case, 2 of those bursts, burst number 1st and burst number 4th. So we actually saved the baseband data. So when we say baseband data, it is a raw voltage data. Okay. Like, telescope saves data in forms of binary numbers and all, but then we cannot save all those like voltage data. So we basically compress it and save only important one, like combine different polarizations and all that. So for these 2 FRBs, we actually saved the baseband data. So what it means is we are able to get better localization compared to those FRBs where we actually saved only intensity data, means combined data. So that's what, if you go to figure, just to show you what the localization region looks, we can actually go to figure 3. Mm-hmm. I hope I'm right here.
I'm going to go. Yes, well, we're going to talk about that.
Exactly. That's right.
Okay.
So this is the red ellipse you see here. It is the 90% confidence localization region. So in Bayesian terms, we can say that we are 90% confident that the FRB is within this ellipse. Now, so one thing that you see when you have when actually you look at this field of view is there exists a galaxy, a very bright galaxy, a nearby galaxy, which we call Messier 81 or M81 in short. And it is one of the closest bright galaxy to the Milky Way. It is only at a distance of 3.6 megaparsec. So, you know, Andromeda, the closest massive neighbor to Milky Way, its distance is around I think 0.7 megaparsec. It is 3.6 megaparsec. So it's roughly 5 times. So it's literally in our neighborhood. Now, the thing is, as I said, the dispersion measure excess means when I subtract the ISM contribution, then from the FRB DM, that DM excess is very small. It's in this case only around 40 to 50 units. And if we believe a canonical model for our Milky Way halo, means let's say the simulation suggests that its contribution is something around 30 units. Then if we subtract that as well, then the excess we are left with is only 20 units roughly. Now that 20 units, I forgot to tell you that in the case of FRBs, we know that this DM excess, the extragalactic DM, when we subtract the Milky Way halo and Milky Way disk contribution from the DM, that is somewhat an indicative, it indicates the distance of that FRB from us.
I'm with you.
So in this case, the 20 units suggest that the FRB should be in quite nearby, like within 135 megaparsec. So it's in the local universe for all practical purposes. Now we found this galaxy here. So one thing you say that, yeah, this FRB is associated with this with M81.
Right.
But the problem is, if you look at this optical image, you see that this FRB is then, if you believe that it is associated with the M81, just looking at the optical image, we think that, okay, this FRB is in the middle of nowhere. There's no stars, no gas. But many times, and actually it often happens, especially in astronomy, that optical images can be deceiving or can deceive you in the sense that you cannot see all the matter. So in the inset, you can see that 21 centimeter image of this field of view.
Yep.
And there you can see we have a lot of neutral hydrogen gas. And the disk actually extends to the location of this FRB. So this FRB is not actually like in the middle of nowhere. It is in the extended disk of this galaxy.
Mm-hmm.
So that is a great, actually, this is, I was really excited when I saw this image and I saw, yeah, we have something. But the problem here is, you know, whenever you claim something big, for example, in this case, it will be the closest extragalactic fast radio burst discovered today, by far the closest from the next closest one at that time, which was, I think, at a distance of 150 megaparsec.
Yeah.
So it is way more closer.
Mm-hmm.
And the importance of discovering nearby FRBs is that you can study their local environment with great details. You can actually look at the localization region in different bands. You can even see whether we can even detect a very faint repeating burst from this FRB, because your telescopes are sensitive enough. So it's a very, I think it's a very big, what you call, achievement if you detect many nearby FRBs.
Mm-hmm.
But the challenge we had at that time was we don't know our Milky Way halo. So it could be a Milky Way halo object as well. But then if it is a Milky Way halo object, it must be at the outskirts of the halo, and it must be unusually energetic. Means not like anything we have discovered in the radio band.
Fair enough.
So in that case, even that discovery is very significant. So now we have two significant discoveries, like two significant possibilities. If it is a Milky Way halo object, it is at the outskirts of the Milky Way halo and hence extremely energetic and unusual, sort of exotic galactic object. And if it is associated with M81, then it will be the closest extragalactic FRB discovered to date. And also its location is so unusual because most of the FRBs are located that we have discovered to date, and we were able to localize to their host galaxies, were quite near, quite close to the disk. Basically, it's not really far away. So, but this, if you can see that the projected separation between this ellipse and from the center of this M81 galaxy, it is 20 kiloparsec. It is more than 5 times the what you call half light radius.
Yep.
So it's unusual. So in that case as well. So what we did in this paper is we thought that let's take a role of a detective in this case and then see what are possible scenarios. Okay. So we come up with, in general, like if you don't know anything about this FRB, there are 4 possibilities. First, the FRB is located within the Milky Way disk. In that case, it might be a pulsar, because pulsars and FRBs, when you de-disperse, it looks quite same. Yeah. It could be an unknown pulsar. Second possibility, this FRB source is a galactic source, but it is not in the Milky Way disk, but in the Milky Way halo. Okay. Third possibility, it is between Milky Way and M81 galaxy. Okay. And last, but not the least, the possibility is FRB is located beyond M81.
Okay, sure.
So because I estimated the maximum distance around 135 megaparsec, and this galaxy distance, the distance of this galaxy from us is only 3.6 megaparsec. So there is a phase space beyond 3.6 as well. Sure. Now, in this paper, we basically critically analyze all these 4 possibilities, and we came to the conclusion that the most plausible possibility is this FRB is associated with M81. And now I will tell you how we did that. Okay. Now, the first thing is, if you go up, I'm sorry, it's analysis. So the first thing is to check. Yeah. So the first part is to check whether this FRB can be in the Milky Way disk. Now, we basically use different galactic probes. We use H-alpha emission line, we use free emission that we detect in the radio, that we also look at Galax data, we look at mid-IR data to check, to see whether there is any H2 region, because H2 region can provide this excess dispersion measure, and we find none. And the maximum value we estimated that Milky Way disk can contribute is around 40 units. So there is an excess of 50 unit approximately in this case. So the first possibility is rejected. It cannot be in the Milky Way disk. Okay. Now the second possibility is it can be in the Milky Way halo. And I said there are constraints on the number density from of free electrons or matter in the Milky Way halo from different studies, like in optical and in UV, in far UV, we see emission lines or absorption lines of oxygen, carbon and all. So we have some estimates. What I did is, if we consider the most conservative case, like the density of electrons, basically in the Milky Way halo is 10 to the power minus 3, which is high, by the way. So in that conservative case scenario, we found that the FRB should be, if it is in the Milky Way halo, should be around 100 to 300 or 400 kiloparsec away from us. Okay. Now, with this, what we did is we compare, we know some millisecond, because the duration of these bursts are few milliseconds. So there are millisecond pulsars, and there are at least a couple of millisecond pulsars where we have seen giant pulses. And by the way, we still don't know why those millisecond pulsars are able to produce giant pulses, but still we have observations. Yep. But then what we did is we basically do this energetic studies. We say, if this FRB is located at 100 kiloparsec, then how energetic these bursts are, the detected bursts from this FRB candidate. Then we found that it is more than 100 times more energetic than those detected, than the most energetic giant burst or pulses we detected from those millisecond pulsars.
Yes, I'm with you.
In that case, so we cannot reject this scenario, but we can say that if this FRB candidate is within the Milky Way halo, then it must be extremely energetic and by far the farthest, what do you call, detected galactic compact object known to date. So that's why this discovery is interesting, but we don't have all these observational constraints, does not really make this scenario a little, what do you call, tailor-made, or you need to what what you I'm just thinking about the best word. You need to, yeah, we need to tune the plugs and all that to just say that, oh, this is in the Milky Way halo. But the third scenario is it is associated with M81 galaxy. Now this scenario is actually quite promising, and the one reason is we can estimate the chance coincidence probability. Means what are the chances that we find this FRB that close to M81 FRB purely by luck, and that probability turns out to be very small. It is 10 to the power minus 4.
Okay.
Now, but then you may ask, okay, but CHIME is detecting so many FRBs. So it may be like, because you are detecting so many FRBs, then highly unlikely scenario may become likely. So in that case, what we did is we used sophisticated statistical techniques, and we based formalism basically, and then we estimated conservative chance coincidence probability, and that too turns out to be smaller than 1%. So it is very unlikely that we find this FRB by chance that close to the M81 galaxy. So means this, now we have one plus point, means chance coincidence is small. And I didn't discuss here, but there is a Bayesian method of estimating true host association probability as well. And if you apply that formalism as well, you find that true association probability is greater than 99%. So that's another thing. So this is one thing, but then you may argue that are there other ways to actually say that FRBs, that the fourth scenario is FRB may be beyond the M81 galaxy.
Right.
Now, for that, as you see, there is FRB is not actually in the middle of nowhere. There is H1 disk, and H1 disk has means you have particles there, and then there is M81 halo that also contributes. And M81 galaxy is also part of something called M81 group, near a very bright. It's one of the closest galaxy groups. Means it's a collection of more than 30 galaxies, basically. So because those galaxies contribute to the electron density as well, there is the matter in the halo in that group medium as well. So what I did, I'm sorry, that figure is missing. So you need to go back and share the plot.
Our infamous missing plot.
Yes, that's really strange. Thank you very much, by the way, for letting me know about this. I should be more.
For those who are watching, we actually found an error in the paper that somehow one of the figures that was supposed to be in the paper is not in the paper. And so we're going to show the figure that should have been in the paper, and we'll get this straightened out with the journal later.
Yeah.
Let me go ahead and share the missing figure.
That's right. Yeah. So in case now, if FRB source is beyond M81, then definitely M81 circumgalactic medium and M81 group medium would also contribute to that observed FRB dispersion measure. Means that 88 term is not the 88 value now consists of Milky Way ISM, Milky Way halo,
right,
the IgM intergalactic medium between M81 and Milky Way, which is small because M81 is very nearby. And then the contribution from the Milky Way, M81 halo as well. Now, this figure basically quantify that contribution. So what I have done is, so these dotted black and gray line here, close to 20 is the DM excess. We have the fiducial values. As you can see, it is between 18 to 23. And then I have actually studied and used different models, different proposed halo models, and then estimate what DM contribution those model predict for M81.
Okay.
Now, we know that, as I told you, the FRB ellipse is the projected offset of the FRB ellipse is around 20 kiloparsec. So that's why the dotted vertical lines tells you it's between 18 kiloparsec and 24 kiloparsec. Now, that's right. So what I've plotted here is the prediction, the DM halo prediction for the M81 halo. Okay. So as you can see, all the models basically predicts more than the excess DM we have.
Yes.
So it means that it is highly unlikely that FRB is beyond M81 galaxy.
Right.
Because 88 DM units, and if it is beyond M81, then you expect at least 30 DM units. Okay. Which is the most conservative model, but your DM excess is only 23 at max. So it's unlikely that the FRB is beyond M81. So now, so at the end of the day, we only have two possibilities. One is FRB is within the Milky Way halo at the outskirts, it's an isolated exotic object, or it is associated with M81. Right. Now, I already gave you two strong evidences in support of M81 association that we have reported in the paper. One, the chance coincidence probability is extremely low.
Right.
And second, it cannot be beyond M81. And if you invoke Milky Way halo, then that object is really exotic. And we need to fine-tune things to actually make sure that it lives in the M81 halo. And then the constraints from different models, proposed model for Milky Way halo is not very strong. So in that case, now there are third important, I think, significant evidence to support the association of this FRB with M81. So can we go back again to figure 3?
Sorry about that. There we go.
Now, within this red ellipse, we actually found a few M81 sources. So see, so these exactly. So source number 3, 4, 1, 2, 3, 4. These sources you cannot see in the optical image, unfortunately, because it's a DSS image. These are not sensitive, but there are catalogs available already, and most of those catalogs are basically AAS papers that I'm citing here. So you can see these sources. So we found interesting M81 sources ranging from an X-ray source. Or H2 region, or source number 3 is a globular cluster, and then source number 4 is a persistent radio source, just like so these are interesting sources, and different FRB models actually suggest that FRB sources are most likely associated with one of them. So we have interesting M81 sources as well. It's not that it is in the middle of nowhere. There are sources available, and so then all these, if you basically add up all these observational evidences, you actually associate this FRB to M81.
Yes.
And if you basically believe other host associations that have been made so far, you see that these evidences for them are strong enough to say that this is M81 source. Yes. But as I said, in this case, we actually consciously decided that we'll not say that it is M81 source, just because this unlikely scenario that it is at the outskirts of M81, sorry, outskirts of our own Milky Way, is also very interesting. It's a significant, it will be if it is true, then it will be a significant discovery in itself. So we see that it is likely that this FRB is associated with M81, but we cannot conclusively reject the possibility that this FRB basically is located at the outskirts of our own galaxy. Okay. So that is the, I think, crux of this paper. And then in discussion session, I basically discussed individually what are these sources, source 1, 2, 3, and 4, compare it with other this galactic FRB-like event happened in 2020 that we know is associated with the magnetar. So that is basically we did in the discussion section, and yeah.
Very cool. Very cool.
So
nice. All right. And then we end off with the summary.
Yeah.
Very cool. Mohit, I want to thank you very much for walking us through your very lovely, if missing figure, AP letter. That is very awesome. So let me ask you, since this is a very hot topic, FRBs is a hot topic, and certainly Chime is leading a charge. So where do we go from here? Where do we go? Where do you think we go over the next, let's say, 5 years on FRBs and chimes? Are there additional nearby sources? Are there other tests that could be done to firm up the conclusion that it's related to M81? Are there other nearby ones associated with other nearby galaxies? Just give it a future look on where things might head over the next 5 years.
Yeah, sure. Thank you very much for asking this question, Frank. So I'll start with the topic that is very close to my heart, means nearby local universe fast radio burst. And I firmly believe that in order to understand the progenitors or sources of fast radio bursts, these are the best sources we have. So that's full stop. So this is my firm belief. And now we're talking, so we are talking about M81, FRB, this one. Now, later, I think after 2 or 3 months, when I put this paper on archive, we actually found we are able to localize this FRB to an M81 globular cluster. It's source number 3, by the way, in the ellipse. So this source is exactly within the ellipse and the one that we have actually cataloged in this paper. And we mentioned in this paper, I think if you read that section, we said that though globular clusters means we don't know whether these can be an interesting sources of FRBs or not, but the presence of one within the localization region is definitely noteworthy. And it comes to a great surprise to us, happy surprise, I should say, that this FRB is found to be associated with that globular cluster. The paper is in review right now. But talking about other nearby FRBs, I've recently I led a paper that is recently published again in FJL, where we found the second closest repeating fast radio burst. It is within our own supercluster, Laniakea. It is at the distance of 20 megaparsec. So still, we can actually do this very sensitive follow-up studies. We can look for X-ray counterparts, like many models, many proposed FRB progenitor models actually suggest that you actually see persistent or maybe prompt or afterglow emission in X-rays and maybe in radio and in optical. So these are the sources that you should target, and you should basically look in different bands. Cool. And so I think, and I actually believe that, and there is some, I'm also currently doing analysis of other nearby FRBs, which I hope I'll publish soon. So I believe that by the end of the next year, we actually have good number of sources, nearby sources, and those sources are, I suppose, we follow them up and then we localize them and then we study.
So you must get some sort of a prize for FRB Hunter of the year or something like that.
Yeah.
Cool. So let me ask you a dangerous question. Given that we're now detecting FRBs relatively close and even localized enough to say they might belong to this globular cluster or something else, what's your projection for when we will figure out what FRBs actually are physically?
Oh, that's a very good question. Now, to be honest, so the way I think about this problem is, first of all, we know that the sources of fast radio burst must be exotic, because in the Milky Way, we haven't seen any source that can produce such an energetic burst. Now, there are models that propose that
Sure.
these are magnetars, basically high magnetic field, and maybe in some cases spinning with the period of around milliseconds. And those models are proposed to be produced from cataclysmic events like binary neutron star mergers, binary white dwarf mergers, or explosions, type 1a supernova explosions that may result into a magnetar. So the thing is, so FRBs, if it's true, then FRB sources are indirectly mapping the progenitors or end product of these exotic events. And if we are able to pinpoint that the FRBs are, let's say, neutron star or magnetar with certain property, we're actually able to constrain these exotic
Channels.
phenomena as well. And with that, we can actually see whether, now, because we also study the local environment of these FRBs, and whether we see whether what kind of elements are there in them, whether there is a H2 region or something, then in some way we are also able to constrain the type of stars we need to form this. So you see that indirectly, by doing this reverse engineering, we can actually able to constrain the evolution and dynamics of different stars. We can study those stars, which maybe in the Milky Way right now we cannot find them. So I see it has this field will have a huge impact on our understanding of how stars form, die, and what sort of exotic or extreme events that occur in the universe. So to your question, I feel that from next year onwards, we'll have chime FRB outriggers start operating in that. So those outriggers, basically they're small chimes, but they're located hundreds or thousands of kilometers away from each other. So what we do is once we detect an FRB with chime, we are able to localize that FRB to a milli-arc second precision, because this also save baseband data at these small chime telescopes. Mm-hmm. And then we just perform a localization, and then we can exactly study where in the host galaxies these FRBs are. So we know the redshift, we can study the local environment, we can follow up them with different optical or X-ray or other telescopes. And if there happens to be nearby, we can actually see, because LSS also will be functioning soon in 2023, and by that time and all, we can cross correlate with these compact the events, the interesting transient events that are detected in optical and radio and other telescopes. So by doing that, we can actually pinpoint what kind of progenitors these FRBs favor. I think so. Next 2 to 3 years, I actually feel will be very promising.
Okay, I heard a number, 2 to 3 years. Very cool.
I'm saying 2 to 3 because it's during my duration of postdoctoral fellowship. Maybe those who are listening to your program will say that, yeah, hire him as a postdoc.
Very nice. Awesome. Thank you again for chatting. And everyone, I hope this made your astronomy day just a little bit better, and we will see you on the next one. Okay, thank you. Bye-bye.